Hi, this is Bruce with Z Group Energy, Coolidge, Arizona, with our March 9, 2018 supercritical geothermal energy update asking, why does the Earth produce geothermal energy? Another way to ask might be, why is the center of the Earth so hot? Earth's spherical structure is composed of three major components. You can see those in the picture there. A relatively thin crust at its surface, a thicker mantle beneath the crust comprising most of Earth's volumetric mass, extending from the upper crust to the center core. And the third component is the core at its center, having a liquid outside with solid center. The middle mantle portion consists of both solid rock and softer rock, depending on cooler or warmer temperatures. The crust and upper mantle are referred to as the lithosphere, which is underlain by a zone known as the asthenosphere. Portions of Earth have a relatively thick surface layer, primarily composed of granitic rock called the continental crust. This portion of the crust underlies our continents. A thinner oceanic crust, primarily composed of basaltic rock from volcanic lava, forms the bottom of our ocean basins. Interestingly, the lower density continental crust, made up of individual pieces called plates, float on the higher density mantle below, just as oil floats on water. The crust portion of Earth is of interest for geothermal heat harvesting. The crust beneath the continents averages 30 kilometers in thickness, that's about 18 miles, and the thinner oceanic crust portions are about 5 kilometers thick, about 3 miles. Geothermal exploration currently does not exceed 16 kilometers, that's about 10 miles, and in most instances is significantly less than that. The deepest geothermal well in Iceland, for instance, is drilled to about 4,600 meters, where it reaches supercritical temperatures and pressures. Earth's mantle is approximately 2,900 kilometers thick, that's about 1,800 miles, extending from the upper crust layer to the outer liquid core, and it's primarily composed of olivine-rich rock. Temperatures range from 500 degrees to 900 degrees Celsius. That's about 932 degrees to 1650 degrees Fahrenheit. That's near the crust, to more than 4,000 degrees Celsius at the bottom liquid core boundary. That's over 7,000 degrees Fahrenheit. Earth's internal temperature gradient, also called a geothermal gradient, increases with depth, though not linearly. This temperature gradient within the upper 100 kilometers or so, that's about 62 miles, is fairly uniform within a given tectonic area, but it varies widely between tectonic areas, increasing on average by about 15 to 30 degrees centigrade per kilometer of depth, then suddenly increasing more dramatically through the mantle. You'll see that in a later slide. The variable geothermal gradient causes rock to behave differently, resulting in two separate rock zones within the mantle. Rock in the upper mantle is cooler, it's brittle, and cracks under stress, which produces earthquakes. Rock lower in the mantle is hotter, and it's softer, so it deforms and convectively flows under stress instead of breaking apart. Earth's core is thought to be composed mainly of an iron-nickel alloy. This assumed composition is predicated on meteorite densities, which are typically iron-nickel alloys, and meteorites are thought to originate from interiors of other planetary bodies. The core is Earth's source of internal heat because it contains radioactive materials, releasing heat as they break down into more stable substances. The core is divided into two different zones. The outer portion of the core is liquid because temperatures are adequate to melt the iron-nickel alloy. The inner core remains solid, even though its temperature is higher than the outer core, because extremely high pressures developed by the overlying rock burden prevent expansion into the liquid phase. You can see in the graph on the left the thermal gradient, and you can see up near the surface it's very almost horizontal. There's not much angle to it, and then suddenly it just drops down through the mantle. Anyway, Earth's interior heat arises from two basic sources, each contributing about half the total heat. The first source of heat results from retained heat of friction resulting from the collision of particles originally creating the Earth, plus subsequent frictional heat caused by gravitationally driven convective redistribution of material within the mantle, for example, heavier elements like iron sinking toward the core. It's difficult, really, to imagine Earth's interior convecting. This convection is typically associated with liquids, where cooler, more dense fluid sinks and warmer, less dense fluid rises, forming a convective flow pattern. Earth's mantle is made of rock, but nonetheless, it's so hot as to be sufficiently plastic, slowly deforming and very slowly flowing. Now we're talking here about mere centimeters annually, so the movement is very slow, very incremental, where the hottest, least dense material near the core rises through cooler, less dense mantle material away from the core in a very slow convective pattern. This convective flow within the mantle is responsible in large part for continental movement and what are known as plate tectonics and continental drift. Most of us have heard of that. For our purposes discussing geothermal heat mining, we're concerned only with the upper portion of Earth's crust, say the topmost 10 miles, or usually less. Certainly not more than that at the moment. Earth's radius from surface to core center is approximately 6,400 kilometers. That's about 4,000 miles, of which the upper crust portion beneath the continents averages, as we mentioned earlier, about 30 kilometers. That's 18 miles in thickness, and the thinner oceanic crust portions average about 5 kilometers thick. That's about 3 miles. Now, the second heat source is spontaneous radioactive decay of various elements such as uranium-235 or 238, potassium-40, thorium-232, and so on. And these occur mostly within the mantle, the lower portions of the mantle and the core. It should be noted that as these radioactive isotopes decay or are used up, so to speak, the heat produced slowly decreases, meaning Earth's interior is slowly cooling. It's estimated that roughly 25% of these isotopes have been exhausted since Earth's formation approximately 4.5 billion years ago. And we don't need to worry about that, do we? Temperatures range from 500 to 900 degrees centigrade near the crust to more than 4,000 degrees centigrade at the liquid core boundary, and more than 5,000 degrees Celsius, that's about 9,000 degrees Fahrenheit, at the core center. Earth's internal temperature gradient increases with depth, though not linearly. This temperature gradient within the upper 100 kilometers or so is fairly uniform within a given tectonic area but varies widely between tectonic areas, increasing on average by 15 to 30 degrees centigrade per kilometer of depth, then increasing more dramatically through the mantle, finally heating up more slowly approaching the core. So, how do we collect all this heat energy? The amount of heat stored within 10,000 meters, say 33,000 feet of Earth's surface, contains approximately 50,000 times more energy than all oil and natural gas resources in the world. Now, areas having the highest underground temperatures occur near active or geologically young volcanoes. These geothermally productive hotspots occur along tectonic plate boundaries or where crust thickness anomalies are thin enough for the heat to rise closer to the surface. We currently harness Earth's thermal energy using conventional geothermal methods. You can see a graphic representation on the right here. Harvesting hot subsurface fluids from below ground reservoirs, using those fluids directly to drive steam turbines and turn driving generators producing electricity. In other words, thermal energy is converted to mechanical energy and finally to electrical energy for distribution to the grid. Conventional direct harvest of geothermal brines as practiced today frequently necessitates expensive treatment to reduce equipment damaging corrosion and or toxicity of the below ground brines. Now the proposed ZGE system doesn't harvest subsurface liquids at all. Instead, heating internally contained, convectively flowing, clean water by conduction, and it does this by taking heat from surrounding hot rock, whether that rock is wet or dry. The ZGE sealed geothermal system conductively heats and recirculates clean internal water within open-top heat cylinders. You can see those on the left there, extending down to the hot rock from the exchange chamber. Those heat cylinders convey heated water convectively from multiple cylinders to an exchange chamber at ground surface where multiple cylinder discharges are homogeneously mixed and then discharged to a pressurized storage container and finally to the turbines for generation of electricity. Most significantly, this can all be done using supercritical water to generate electricity for about 0.036 euros per kilowatt hour, or about 0.045 cents per kilowatt hour. That's about it in a nutshell. If you'd like to learn more about ZGE's closed system, supercritical technology for mining Earth's heat while leaving those troublesome subsurface fluids behind, please visit our website at www.zgroupenergy.com. We'd sure love to hear from you. Thanks so much for listening.